Okay. All right. So test 2 material. Now what we're doing now is there are two sections. Well, let me just see a raise of hands to see anybody in the room. Is anybody from Dada's section? Anyone? Okay. You? Just you? Okay, no. If you hear anybody, I'm interested in giving a review session for Dada because Dada's material is slightly different from what you guys are doing. So for test 2, it's chapter 5, which is about rotation. Chapter 6, which is about energy. And chapter 7, which is about momentum, collisions, and a brief center of mass. Okay, so those are the big overviews. From what I understand, his test is going to be outlined like 8. Now, if you hear otherwise, let me know and then I can adjust. 8 multiple choice minimum. When he rolled out those, when I heard there was only going to be 8 5-point multiple choice problems, I was like, ooh, that could be bad. Because the problem with the multiple choice is that you can't get partial credit. It's an all or nothing. I think he's also had the problem with not doing Scantrons. There was a lot of incorrectly marked problems. So with going with the Scantron, he can just fix it outright. Plus, scanning Scantrons takes about 5 minutes for 350 students. I think there'll be more. I want to say there'll be more. 8 minimum. When I gave a test, it was 25, but each one was 2 points each, and they were more like physical science questions. He's going to have, he said 2 problems? I've heard 2. Oh, more this time? So probably 3 problems, and then 1 bonus. Now, the bonus is really good, but the bonus can be really bad. One of the problems that I've had with the bonus is I initially thought that giving the bonus would help everybody out, but the problem is that it helps the students who are going to do good anyway, and it just boosts them up. And then what you get is you don't get a bell that moves like this. You get a barbell, which I don't really think is kind of a good thing. But we got to take advantage of the situation as it's presented to us. So for the bonus, I've heard a lot of wild, crazy things. I've heard, I think, this is kind of a general overview initially. I think there's going to be an elastic collision problem. And we'll go over that. I think that there's going to be an energy problem dealing with gravity, springs, and or friction. And then for rotation, it's going to be, my guess is, it's going to be obviously circular motion. Either with gravity. If it's gravity, that'll be an actual problem. If it's ball on a string, I could see it be more of a either a multiple choice or something like that. I think that with momentum, center of mass could definitely be multiple choice, but we're going to treat it like a real problem so that we can understand it. And then impulse, playing with the fact that delta P is delta T times F. And so what we're going to try to do is, with starting on such a broad subject, what I'm going to do is I'm going to kind of give a streamlined, abbreviated view of each of the chapters. That'll take about an hour, and then for the following hour, we'll focus on problems. And so that'll kind of be the general outline of the whole thing. One thing that you need to think about in terms of the multiple choice is the way that I treated my tests. The problems were to see if you understood the general how to get the problem done. And then the multiple choice I used to test your depth of knowledge. And so it was really critical. A lot of people thought that the multiple choice was kind of throwaway. But for me, there were some really subtle questions that I would ask a student just to see if they really knew what was going on. And because there were only 2 points each, I felt that that made the difference between the A and the B students. So for rotation, initially we had in the linear world, we had that the sum of the forces in y or x is equal to 0. And this is translational equilibrium. In the case of circular motion, the sum of the forces are in radial, and that is mv squared over r. Whereas in the linear world, the sum of the forces is equal to 0, or if A is non-zero, then we have sum of the forces in y is equal to ma. So in the case of this, it still is ma, but this is mar, where ar is radial acceleration. Now for this circular motion, if you have a circle and an object is moving in that motion, if it is on the right side of the circle moving counterclockwise, that velocity vector is straight up. If it is here, then that velocity vector is to the left, and that the velocity vector there is down, and the velocity vector there is to the right. So in each of these 4 cases, the velocity vector is pointing in a different direction. So what does it mean if you have a velocity vector that's actually changing, that's not constant? There is an acceleration, it does exist. A changing v means there is an acceleration. We just started. So a changing v means there is an acceleration. This acceleration is radial acceleration. Now radial acceleration, we're about to see how well the colors do on this. So those radial accelerations are pointing inward. Let's see if I can. Whoa, there we go, better. So the radial accelerations, AR, and we can treat them as vectors, are perpendicular to V. They radiate inward. And this AR is equal to V squared over R. Now, like regular acceleration, AR has the units of m squared over seconds. So we get meters squared, or I'm sorry, why? Why is no one's bothering me with this? You should be screaming at me. Meters per second. Duh. Why would I say acceleration is meters squared per second? Because I don't know what I'm talking about. I'm an old man. So the radial acceleration is meters per second squared. And let me turn these off. So if you had an object, just as a simple example, and that radius is 20 meters, and let's say that the period was 12 seconds. So just as a review, capital T is period, and it's the time for one rotation, whereas F is the frequency, and it is the number of rotations per second. So for time period is the time for one rotation. F frequency is the number of rotations per second. The relationship between the two is that. The unit of period is just a simple second. The unit of frequency is a hertz or inverse second. And I'm really big on units. You know your units, a lot of stuff will come into place. So in the case like this, you have a circle where an object is moving once every 12 seconds, which means your frequency is 1/12 hertz. And then, if I could ask, well, what is the radial acceleration and what is the velocity of the object around that circle? Well, the radial acceleration, well, is v squared over r, but I also know that v is distance over time. Well, what distance are we talking about? We're talking about the distance around one rotation, or one circumference. The time for one rotation about its circumference is the period. So circumference is 2 pi r, and the period is 12. So it is 2 times pi times 20 over 12, and that gives me, I don't know. So 10.5 meters per second. I got those units right. Now that I have my velocity, I can get my radial acceleration. The v, 10.5 squared over r, which is 12, (9.14 meters per second squared. And so that is a simple rotational motion problem. We have questions? Yes?
What should be the shorthand of that one? Over R? V squared over R?
Oh, yes. Hold on, whoa. Yes. What was 12 originally for? The period. Okay. So that changes that. .51. That makes it better. Okay. All right. So that is a circular motion problem. And one of the things that they can use for that I've seen on a regular basis from homework assignments is a ball on a string and planetary motion using gravity. So for a ball on a string, you have the circular motion here, you have the ball, it's tied to the center. For planetary motion, you have the big mass 1 in the center and the little mass 2 on the outside. The ball on the string is a more simple problem. It's in stable circular motion, which means that the sum of the forces is equal to MAR, which is equal to MV squared over R. For planetary motion, it's also, and I really should be consistent with my subscripts, that's little r. You can actually use little r or big R, but once you pick a letter, you need to stick with it. MAR, which again is MV squared over R. Now, this is what they equal, MV squared over R. The difference is the sum of the forces. So what's hiding within the sum of the forces are the forces themselves. In the case of the ball on the string, it's the tension. And I apologize for the confusion in units because big T is typically period in this case. For planetary motion, it's the force of gravity pulling in. That the central mass is pulling at the mass that's orbiting around it. Well, what these forces are, in the case of the ball on the string, is tension. So MV squared over R is simply capital T. In the case of planetary motion, MV squared over R is equal to capital G, M at the center, R squared. That this M, the little m, is the orbiting mass and mass C is the central mass. Now here, the orbiting masses cancel. So the actual mass of the satellite is not relevant. One of the radiuses cancel. And so you're left with V squared equals capital G central mass over R. And so it all depends on what he asks for. He could ask for the period of the motion. He could ask for the frequency or the central mass or the radius. And so all you have to do is solve for one of these items. Typically what they do is they substitute V with distance over time, and that becomes circumference over 2 pi r. So v squared is c squared over 4 pi squared r. What did I just do? Hold on. No. Okay, so the v is that, or the v squared. So 4 pi squared r squared over period squared is equal to GMC r. And now you can solve for anything, and typically this is where the r cubed comes from.
So this is for the planetary measurement?
Yes. Okay. And what I did is, my mistake was I substituted 2 pi r for t because I was making an association between circumference and what it actually meant. And so this is where you can go with, you can solve for period, you can solve for radius, you can solve for the central mass, you can solve for any of those things. One of the last things that we're going to cover for circular motion is I call it the gravitron. And if you have a mass, so this is down, where gravity. So here we have the force of gravity, and at the top we have the force of gravity. If you've ever been on the carnival ride, the Gravitron, you walk into a circular area, you get strapped to the wall, and then the thing swings around, and eventually it goes vertical. And so you're getting swung around like this. And so at the bottom, you have the force of gravity pulling down as well as the top. Because you're moving in a circular motion, the radial acceleration is always inward. And the normal force, the force of the wall on you, is always inward. And what we're going to do is we're going to describe why you feel heavier at the bottom than you do at the top. So at the top, the sum of the forces radially is equal to negative MAR. It's negative because AR is down. One of the things that I do frequently is, if it's pointed down, I like to keep my negative signs out front where I can watch them. If it's up, it's positive. Down, negative. That's why in this case, pretty much the only exception, well actually you guys use 9.81 or 9.8. Two-dimensional motion is not, two-dimensional motion is kind of the aberration. That's where you use the negative 9.8 for acceleration. Pretty much for everywhere else, you use 9.8 consistently as a positive value. So this negative MAR is equal to minus Fn minus Fg. So the normal force is equal to MAR minus Fg. Now at the bottom, the AR is pointed up. So the sum of the forces radially is equal to positive MAR. and that is equal to positive Fn minus Fg. So that the normal force is equal to MAR plus Fg. And so what this shows is that the normal force, the force of the wall pushing on you, is higher at the bottom than it is at the top. This is why you feel lighter. That sense of being light is the reason why, well, it's basically because you're getting slung over and gravity is trying to pull you down as well. And when Fn is equal to 0, you are weightless. A perfect example of this is when you're on, they call it the vomit comet. It is, if you've ever seen the movie, Tom Hanks starred in it, it is Apollo 13. And they have frequently scenes of them floating weightless and they're passing up people, other things, and there was no special effects involved. What was happening was that the plane would arc in a huge arc, and for a brief, like about 2 minutes, it would be free fall. And then it would get to the bottom of the arc, and everybody would experience gravity of 2 Gs. And then it would go up again, and it would be 0 Gs, and then it would repeat. And they recommend you don't eat before you get on the flight, because stomach contents don't do well in 0 G, and then 2 G, and then lather and repeat. So this is one of the reasons why you feel weightless, is because for a brief period you're accelerating downward with gravity and you feel lighter. So that's it for circular motion. Basically the core equations will be this. Yes?
So will whenever the force, normal force is 0, will it be a plus or will it be like a
If he said weightless, then that would be kind of inferred. It would be inferring, not sure. I'm not English major. There was another example of you're on a scale in an elevator. So all three cases, you have a normal force and a gravity force. In the case of this, there's no acceleration. In this case, acceleration is up. In that case, acceleration is down. And in these three cases, the sum of the forces vertically is equal to 0. In this case, the sum of the forces in y is equal to positive ma, and the sum of the forces in y is equal to negative ma. So one of the things that you have to know, and it will be stated or inferred or told to you, is are you accelerating upwards? Are you accelerating downwards? Are you remaining at the same level? In this case, normal force is up, and gravity force is down. So in this case, Fn is equal to Fg. And this Fn is your weight. In this particular case, A is positive or up. You still get Fn minus Fg. And in this case, Fn is equal to Fg plus ma. Your weight has increased. If the acceleration is upwards, your apparent weight goes up. As an example, if you walk into an elevator and you hit the button and the elevator starts moving upwards, what do you feel? You feel slightly heavier. Your apparent weight increases because it's trying to accelerate your body upwards. For this case, once again, it's still Fn minus Fg. So Fn is equal to Fg minus Ma. And so in this case, your apparent weight goes down. And likewise, if you're in an elevator that comes to an abrupt stop, it decelerates. What do you feel? Slightly lighter. So these are the things that you think about when you're doing the circular motion with the gravitron, with the vomit comet, with circular motion where gravity is. You've got to pay attention to where that radial acceleration is going. That determines that sign right there. And then you look at what forces are contributing to that acceleration, and that determines the positiveness and negativeness of the whole thing. And if he said, I would say, just as we're going to get to it with collisions, if he says the word stick, it's inelastic, done, end of discussion. If he says the word weightless, that Fn is equal to 0, as far as I'm concerned. If it's weightless, it's either in free fall or there's no normal force. He's just suspended there. All right, next. Now what we're going to do is we've generally covered circular motion, and now we're going to move on to energy and friction and all that stuff. So work, which is W, is force times distance. Now force is a Newton and distance is a meter. So the units of work are a Newton meter. Another way that you can describe it is that a Newton is a kilogram meter per second squared times meter, or kilograms meter squared second squared. The other way that you can talk about this is that it is a joule. So we have that. Now, more importantly, this F, it is the force that is parallel to the motion. So sometimes I write it like that. And if we're first, as an example, is we have a mass here and you move it a distance d, and the force vector looks like that, then the work is force times the distance that it moved. However, if the force looked like this at an angle, but it still moved distance d, the force we use is the component of F parallel to the motion. in this particular case, what we're looking at is Fx. So this is F, that is Fx, that's theta. So cosine of theta is Fx over F. So Fx is F cosine theta. And so this is why you see that the work is frequently mentioned as Fd cosine theta. And this is the amount of energy that is either going into the system or out of the system, depending on the situation. When we think about energy, there is energy of motion and there is energy of, I don't know what that was, potential. The energy of motion we call kinetic energy. It's the energy that's doing stuff at that particular moment. And then there is potential energy, which has the potential of doing stuff. Now, what we're dealing with in terms of energy, the major kinds are kinetic. Now, my notation is obviously a little bit different from his. My kinetic energy, I just say Ke, and that's 1/2 mv squared. For potential energy, the potential energy comes from spring, which is 1/2 kx squared. And then there's the potential energy of gravity, which is mg. So we get all of this. Now, before we continue, we need to talk about springs for just a moment. If you have a spring and it is attached to something and it's just sitting there doing nothing, it is at its rest position. Now you can do two things with a spring, well, three. One, leave it alone. Two, stretch it. Or C, compress it. If you stretch it, it looks like this. If you compress it, it looks like that. If you stretch it, its displacement, x, is to the right. And if you compress it, its x is to the left. If you stretch it, it will have a force that opposes that in the opposite direction. If you compress it, that force pushes it back to its rest position, which is causing it to expand. And this is the fundamental observation that gives you F equals negative kx, and this is Hooke's law. That basically that the force is always opposite of the displacement. If you displace it to the right, force is to the left. If you displace it to the left, force is to the right. Now, what I tend to deal with is magnitudes. If you have a spring that is stretched, and let's say we put a 50 kilogram mass on the end, and its displacement or distance, because now I'm going to think of it as a distance, that distance is 15 meters. It's stretched really far. And what you do is you look at the forces. Now, the spring force is up. The gravity force is down. What is it doing at this particular moment? Well, it's just sitting there hanging. Well, if it's sitting there hanging, that means that it's doing nothing, which means, and a lot of people go, well, it's doing nothing. I don't understand anything about this. I can't get anything from it. By the fact that it's doing nothing, it's in translational equilibrium. It is giving so much information about it. So that the sum of the forces vertically is Fs minus Fg, which is equal to 0. Or Fs is equal to Fg. So Kx is equal to mg. Well, what about the minus sign? Well, I took care of the minus sign because the spring force is up. So I'm only dealing with x as a distance. So I'm not really worried about it. Because the thing is if I consider gravity to be negative, then I got negatives of negatives, and then I get confused and just want to go to the bar and just be done with it. So with the negative signs, I like to get rid of them. I like to keep them out front because they're shifty and can't be trusted. So that's why I tend to use logic of up and down as positive and negative. Yes?
Why is it so close to 0?
Because at that particular point, the mass is just sitting there doing nothing. So if it's doing nothing, then the sum of the forces has to be nothing, because if the sum of the forces was positive, it would go up. If the sum of the forces was negative, it would go down. So the fact, I mean, as an observation, your coffee cup right now is in translational equilibrium. How do I know? It's not going into the floor, it's not going into the sea. So you just observe it.
How did you get rid of the negative sign again?
I got rid of the negatives. You waited until I sat back down. I got rid of the negative signs because what I deal with when I'm thinking about the physics of stuff, I know that up is positive, and I know that down is negative. And so if I have a spring force pulling up, that spring force has to be positive. So what I do, I mean, you can use Hooke's law with the negative kx, but you've got to do a negative of a negative to get it back to be positive, which now starts getting confusing. So if I know that the spring force is up, that spring force has a magnitude of kx up. Gravity is pulling down, so mg is down negative mg. And that's how I do it. So you can wait until I sit down again. So, all right. So with this, the potential energy is 1/2 kx squared. And that k, looking at this, is mg over x. So m is 50, g is 9.8, and x is 15. So this is going to have a really 32.7. Now, one of the things that a lot of people do is they sit there and go, well, what units are the spring constant? And they get confused, and then things spin out of control. Well, take a look at just Hooke's law. Don't pay attention to the minus sign. Divide both sides by x. Oop, I didn't divide by x. What kind of nonsense is that? So x. F is what? Newtons. X is meter. So the units of the spring constant are newtons per meter. So, dumb question number 1. I got to work over here since I've been over there. I got this spring. The spring constant is 32.7 newtons per meter. I take the spring to the moon, where moon's gravity is 1/6 that of Earth. What's the new spring constant? What's K? You say K out loud. What is K? Not in units, just the thing. The spring, let's say it out loud. Spring constant. Did it say spring? Now, here's one of the things about learning. By me making you feel slightly uncomfortable, do you think you're going to forget this tomorrow on the test? No, I don't think so. So now, because that's how learning is, you got to be slightly uncomfortable. For spring constant, that spring is 32.7 newtons per meter on the moon, in space. That's why it's a constant. It's not next Thursday it's going to be something else. It's not in space it's going to be something else. It's never changing. So you can take that spring anywhere and you get the same value. What would happen is the stretch distance would change. It wouldn't stretch as far on the moon, and it wouldn't stretch at all in space. But the value itself remains the same. Now for energy, we're running late. All right. With energy, if there is no friction, and you will hear me say this a lot, yay, no friction. If there is no friction, yay, no friction, the initial energy will be the same as the final energy. That the energy, and when I talk about energy, I'm talking about mechanical energy, but I will shorten it to simply energy, the energy of the motion, the physics 213 energy that we're concerned about. We're not going to be concerned about thermodynamic energy. Not yet, and probably not ever in 213, because not enough time. So initial energy problems like this are dependent on its initial and final conditions. So the thing that you need to do especially for initial and final situations is take, for example, we'll do simple things like you drop a rock. So it's dropped. What is the velocity at the moment before impact? We're not looking for the snarky answer, which is 0. It hit the bottom, ha ha. No, we're not interested in that. We're interested in the moment before the rock hits the ground. Well, this is its initial state. This is the final state. In the initial state, it's not moving. And it's at height h. Say it's height h. Its final state, it's moving, and it's height 0. What I tend to do is I tend to pick the lowest point as the height of 0. So what we do is, we first say, is there friction? No. And then we all go, yay, no friction. So energy initial is equal to energy final. The energy initial, well, it's not moving, it's at height h, is the initial potential energy. The final energy is kinetic. There's no potential. So the initial potential energy is mgh. The final kinetic energy is 1/2 mv squared. M's cancel. And you get that. So velocity is square root of 2gh. And one of the things that you can do, and this is one of the benefits, I am a passionate believer in the alphabet soup method, that you need to write these things out letter-wise rather than plugging and chugging. There's a select number of exceptions which streamlines the problem. We'll get to that. But for the most part, if you look at this, G is in meters per second squared, height is in meters. That gives you meters per second. So one of the things that you can do is you can look at your equations and then you can go, does this make sense at all? Well, it pops out in meters per second, so it can't be completely wrong. I mean, there may be a missing constant somewhere, but to first order, it looks pretty good. Solving with energy is what you use to determine velocity the quickest. So now one of the things about test 2, you guys are going to use energy. You guys are not going to use motion. So obviously this is going to be a situation where you use energy. But if you were given a problem and he said, use equations of motion or energy, I don't care what you use, just get me the answer. If he asks for, give me the time or give me the position, you would use motion. If he said, give me velocity, you would use energy as fast as humanly possible. Because it's just the quickest way of getting it done, and that's all that matters. So as an example, we have a mass 5 kilograms. And what this is going to do is it's going to touch on all the bases for this. It's compressed. Oh goodness. The compression distance is 4 meters and the spring constant K is 300 meters. No, not that. Newtons per meter. And we have a frictional area down here where mu sub K is 0.5. The height of the hill is 20 meters. Now what we're going to do is that this particular problem that I'm going to ask about is not one specific problem, but it's more like 8. But it's going to cover everything that we really need to do in order to understand all of the energy problems. So, step 1, what is the potential energy of the spring initially? Well, potential energy of a spring is simply 1/2 kx squared. So this is 1/2 300 x is 4 squared. So this is 2,400 joules of energy. Now, I'm going to put on the next part is after spring decompression, what is V? So what is the velocity immediately after the spring decompresses? Well, the best way that you're going to do this, and I'm going to show you all the points, is you can either say that the kinetic energy at this point is 2,400 joules. Why? No friction during this act. So at the top of the hill, there's no friction. Why? Because I said so. So you could first say, well, the kinetic energy, or 1/2 mv squared, is equal to 2,400. So v squared is 2,400 times 2 divided by m, or v is the square root of 2,400 times 2 divided by m. Do I have the mass? Yes, I have the mass. 5.
How is force related to
All right, hold on. Well, there are two things. One, I treat energy as like a magnitude. So the 1/2 kx squared. Who asked that? You did. Okay. I treated the x as a magnitude because it's 1/2 kx squared, and I only deal with magnitudes really. The other point is, you're perfectly happy to plug in a negative number, but -4 squared will give you the same answer as 4 squared. So in this particular case, it doesn't really matter. The only time I really use those negative signs, the Hooke's law, is when I directly determine what force is. Like if you pull it, hold on, I'm trying to get frame of reference. Pull it to the positive. So F equals negative kx, so the force is going to be negative. But if I want to know what energy, stretching it that way or stretching it this way, all I need to know is the distance. It doesn't really matter. So that's the velocity. Now this is the velocity at top of hill. And one of the things that we could do, just to, I mean, we're really going to explore this problem, is that the potential energy of the spring is equal to the kinetic energy at decompression. So in this case, it's 1/2 kx squared is equal to 1/2 mv squared. Cancel, cancel. K over mx squared is equal to v squared. So v is x k over m. X is 4, k is 300, m is 5. And what you'd find out is that 300 divided by 5, square root it, times 4 gives you 30.98. So if you didn't need to know how much energy you had in the system, that would be the right way to do it, to just grind it out. Now the next question is, what is velocity at bottom of hill before it hits the friction surface? So in this particular case, we need to know the velocity at the bottom of the hill. Here, at the top, there's no motion, compressed, height h. At the bottom, there is motion, uncompressed, no height. Remember that we use the height of h equals 0 at the bottom. So there's no height there. We need a reference point, like when you're doing two-dimensional motion. In two-dimensional motion, you got to pick an origin point. In one-dimensional motion, you got to pick a point like at the surface or something like that. There's still no friction, so the energy initial is equal to the energy final. Now the energy initial, well, that is simply mgh plus 1/2 kx squared. This is the initial potential energy, starts at the top of the hill. This is the potential energy of the spring, so that's gravity. So those are the conditions at the top, and they are equal to the kinetic energy at the bottom, which is 1/2 mv squared. Now the first thing I do, I'm going to look for v, solve everything by 2. 2mgh plus kx squared is mv squared. Divide by m. 2gh plus k over m x squared is equal to v squared. Square root 2gh k over m x squared, that's equal to v. And so that's the answer. So we get square root of 2, 9.8, height was 20, yep, plus 305, 4 squared, square root is equal to v. And this is 9.8, not 98. And I get 36.8 meters per second. And so that is the velocity at the bottom of the hill. So remember, what we're doing is we're taking everything one bit at a time. So with every time we do something, we've got to go from one step to the other. The last step is the fact that it's initially moving at 36.8 meters per second across the surface, that the coefficient of friction here is, what did I say, 0.5? I think so. Yep. 0.5. And then at the end of the motion, the velocity is 0. So it's a flat surface. I don't think that he would do like an inclined plane with friction. That would be weird. But what I want to do at least is get the flat surface straightened out. So when you're doing this, a lot of this is a lot like the motion of, you sum the forces vertically to get 0. And why is that? Because you're going to find Fn. Now these are a lot of the steps where you're going to find when you do friction force for motion and stuff like that. Well, you've got, in our little force diagram, Fn up, Fg down, friction force to the left, because velocity is to the right. I don't attach velocity to the force diagram. I use it as a reference point because the velocity is not a force. So this is Fn up minus Fg down. I am letting the directions determine the sign. I'm not letting G, I will not allow G to be negative because then I got to deal with it in all sorts of weird ways. So Fn is equal to Fg. So that means that the normal force is equal to mg. Now, the next step is friction force is mu sub k Fn, because we're going to find the friction force. So to find the friction force, it's mu sub k mg. And then we're going to use work equals force distance. And then what this is we're going to find W, which in this case is the energy dissipated by friction. Which means that the friction force is mu sub k mg. So mu sub k mg d. And that's the work. Now, one of the equations that we're going to have to introduce right now, I looked it up there's a variant of it. It's pretty much how I deal with all the energy problems whatsoever. Because typically in problems like this, the force is always dissipated. And to do this, I call it, a variant of it is 616A on page 157. And I'm going to simplify it in this case. Now, what I'm going to do is I'm going to write this equation in a way that I think is better, because you tend to... Everybody? Oh, okay. We're all referring to the books now. Excellent. My general opinion of the book is, so that you can see me up at the front, I think it's a very good idea that you buy the book. Do you understand my opinion of the book now? All right. So, in this, you have your initial energy minus the energy dissipated through friction is the final energy. Now, my little nickname for it, I've been calling it this for years. This is similar to when you look at that equation right there, you'll go, oh, that's it. I call this the checking account equation. In the checking account equation, the money that you have at the start of the day minus the money you spent is the money that you have at the end of the day. Done. Understood. That's all that energy is. And it makes perfect sense now. The initial energy, well, what was the initial energy that we're thinking about? The initial energy is the motion of the object prior to it hitting that friction surface. So this is the kinetic energy at the bottom. Now we could also use the potential energy at the top plus the spring potential energy. It would be the same thing. Minus the work removed at friction equals 0. Now why is that final energy... Ooh, we need to back that up a bit. Or lower it. That would be helpful. Why is the final energy 0? Bueller. Why is the final energy 0 at the end of the motion? It's at rest, exactly. It's not moving. If it's not moving, there's no kinetic energy. The other thing about this, from here to here, the gravity potential energy is the same. So if the gravity potential energy is the same, they cancel out. If there's no change in physical height, you don't have to worry about it.